We're looking at number 11, and we have the polar equation r is equal to 1 minus sine theta, and we want to find the area of the region that is the interior of the region bounded by the polar curve. So we have r is equal to 1 minus sine theta, and let's go ahead and start sketching it from theta is equal to 0 to theta is equal to 2 pi. So when theta is equal to 0, if you substitute 0 for theta here, you have sine of 0, which is 0, and 1 minus 0 is 1. So when you have an angle of rotation that's 0 radians, you get the point with polar coordinates r theta, where r is 1 and theta is 0. And then as theta goes from 0 to, it looks like about pi over 3 here. Well, actually, that would be pi over 2. Sine of pi over 2 is 1, and 1 minus 1 is 0. So let's go ahead and get to pi over 2, which is about 1.57. And you can see that when we're there, we have a point once again at the pole where theta is equal to pi over 2. Sine of pi over 2 is 1. 1 minus 1 is 0. So we have the point with polar coordinates r theta, where r is 0 and theta is pi over 2. And then we keep going. And we have this part of the curve, and then we get to pi, about 3.14, and we know that sine of pi is 0. 1 minus 0 is 1. So when we have an angle of rotation that's pi radians, we have the point on the curve with polar coordinates r theta, where r is 1 and theta is pi. And then we keep going, and now we have points here. And now we get to 3 pi over 2. The sine of 3 pi over 2 is negative 1. 1 minus negative 1 is 2. So you have this point on the polar curve with polar coordinates r theta, where r is 2 and theta is 3 pi over 2. And here you keep going until you get to theta is equal to 2 pi. So this is what we have. We have a cardioid, and we want to find the area of the interior of this region, the region bounded by this polar curve. Now you will notice that we have symmetry here, where we have symmetry with the radial, with respect to the radial line, theta is equal to pi over 2. So you could take advantage of the symmetry, and if you wanted to find the area of the region that's inside this cardioid, you could find the area of half of the region and multiply by 2. So you could do that. That's an option that you have. And if you want to do that, what should you set the limits of integration? Well, you have different options here. One option is you can start, for example, at pi over 2, and you can, for example, if you look over here, if you start at pi over 2, and then you go to 3 pi over 2, you get this half of your polar curve, and you can find the region that's inside this half of the polar curve, bounded by the radial lines. Theta is equal to pi over 2, which would be over here, and theta is equal to 3 pi over 2, which would be over here. So that's one option. The other option is as follows. You can actually consider what happens when you start at theta is equal to negative pi over 2 and go to just theta is equal to positive pi over 2. So if you do that, then this is what you will have. So you can start, actually, we started originally with theta is equal to 0, and we had the point r theta where r was 1 and theta was 0. But you could also start at theta is equal to negative pi over 2. Sine of negative pi over 2 is negative 1. 1 minus negative 1 is 2. So you would actually start here, and the polar coordinates of this point would be r theta, where r would be 2 and theta would be negative pi over 2. So if you sketch the polar curve on the interval from negative pi over 2 to positive pi over 2, you would get the right half of your polar curve. And then, of course, what you could do is you could find the area of this right half and multiply by 2. So you would so this region that you're seeing right now is bounded by the polar curve and the two radial lines, where your first radial line would be, if you have a counterclockwise rotation, your first radial line would be theta is equal to negative pi over 2, and your second radial line would be theta is equal to positive pi over 2.